Hi everyone, this is Dr. Srishmita Yadav. Welcome once again to my channel Orbital. So guys, in last lecture we have learned about the chiral centers, chiral carbon, chiral nitrogen and some essential experimental results also. Like the molecule having the one chiral carbon are always the optically active. But if the same molecule is having the one chiral nitrogen only, it will not be optically active. So from the last lecture it was concluded that having chiral center is not the criteria of optical activity. So what is mandatory for a molecule to show optical activity? We will discuss this in this lecture. So for a molecule to be optically active, the essential requirement is the chirality, not the chiral center. Okay, so to be optically active, molecule must be chiral, not chiral center. Okay, the molecule must be chiral. So what is the criteria for a molecule to be chiral in nature? This term is not having any connection with the chiral center. Correct? So chirality in the molecule, is basically the essential and sufficient condition to be optically active and to show optical isomerism. So what is the meaning of the chirality in the molecule, or what are the essential conditions to be chiral in nature for a molecule? Mind it, I am rewinding again. Chirality in the molecule or chiral molecule has no connection with the chiral center. It may have chiral center or may also not have the chiral center. Means this is not the chiral word, is not the same chiral center word. Okay, so chirality of the molecule, there are two essential requirements for a molecule to be chiral in nature. That means it must be unsymmetrical. Molecule must be unsymmetrical in nature. Unsymmetrical molecule means in the molecule there should be no imaginary plane so that it can be divided into two equal halves like this. The symmetry should not be there. Okay. Second condition, its mirror image must be non-superimposable. Mirror images must be non-superimposable. So if the first condition is justified and its mirror image is not superimposable, then definitely your molecule will be called chiral molecule. And being chiral in a molecule is essential or sufficient condition. Nothing else is required. If your molecule is chiral, then it will be definitely will be a optically active compound. So how to check these two conditions in a molecule? I am giving you a very clear-cut solution of all these things. For a molecule, if we talk about with respect to the symmetry, we are having the two type of molecule. Number one is asymmetrical molecule. Asymmetrical molecule are those in which all the 23 elements of symmetry are missing. Okay? There are all elements of symmetry are missing. Are not present. They are called asymmetrical molecule. And asymmetrical molecule are essentially optically active. They are essentially optically active and will show optical isomerism. Correct? Now, second term, dissymmetrical. Dissymmetrical molecule. Dissymmetrical molecule are those in which all the 23 elements, how many elements of symmetry are there? There are total 23 elements of symmetry. Asymmetrical molecule in which all the 23 elements of symmetry are absent, no symmetry in any way, then it will be essentially optically active and will show optical isomerism. Dissymmetric molecule is something in which all are not absent, only two elements of symmetry are absent. Dissymmetric molecule in which only two elements of symmetry are not present. And these two are POS, plane of symmetry, and COS, center of symmetry. Are not present. Which two elements are absent? Plane of symmetry, center of symmetry. Those are called dissymmetric molecule. And dissymmetric molecule are also, they are also optical isomers, or shows the optical activity. That means if we conclude for being chiral in nature, the molecule is not essentially required to be asymmetric. If it is dissymmetric also, that is also enough to us. Okay? So a chiral molecule is something in which POS and COS is not present. So if we are going to check for a molecule to optical activity, what we will check? We will check only two things, whether your molecule is having POS or COS or not. If any of these two is present, let's suppose molecule is not having POS but it has COS. Okay, these both must be absent. Then only your molecule will be chiral and it will show optical isomerism. Because being chiral is an essential criteria for optical isomerism. So I hope it is clear to you. Having chiral center is not a criteria for optical activity, but being chiral for a molecule, the molecule must be chiral to show optical activity. And to be chiral, it must not have POS and COS. So now I will explain you how to check the POS and COS in a molecule, because if you are able to check these two things, you can easily tell whether your molecule will show optical activity or not. If both are absent, then your molecule is essentially optically active and will show optical isomerism. If any one of them is present, another one is absent, then it will not be chiral and will not show optical activity. Okay, so I hope all the terms are very clear to you. So let's discuss the POS and COS in detail and finish the topic with some examples. Yes guys, so what is the plane of symmetry, yani POS? How to check it? In a molecule, POS is an imaginary plane to which if we draw a line, then the molecule must be divided into two equal halves and they both must be, the both part must be mirror image of each other. For example, if we see our hand is the best example of the unsymmetrical molecule. Because if we divide it by center, a imaginary plane from the center, then it will be divided into two unequal halves. So that means it is not having POS. Either you divide in this direction or either this in any of the plane. If we draw an imaginary line, the molecule must not be divided into two equal halves. If it is getting divided, that means it is having POS. And for being chiral in nature, we don't want the POS. Okay, so what is the POS? An imaginary line that divide the molecule in two equal halves. I am writing here imaginary plane which divide molecule in two equal halves. Two equal halves, and they are mirror image of each other. Mirror image of each other. For example, let's suppose you are having this. Either you are having cis or trans, like this one. This is the trans isomer, geometrical, and this one is the cis isomer. I am going to draw. There is always the POS. If your molecule is having sp2 or sp hybridization, the molecule, what are the sp2 and sp hybridized structures? Sp hybridized means linear. sp2 hybridized means trigonal planar. They both, the structure have the planarity in the molecule. So if nothing is possible, there is a one plane to which they can be divided into two equal halves always. So those molecules always have POS, like one POS, like this is the double bond, so I can cut it from the center. Half molecule this side, half of this side. Means half H and half methyl here, half H and half methyl there. It is simple, like we are just slicing the bread piece from the center. Like this is a bread piece and this is the thickness. Let's suppose this is the thickness. And I am slicing the bread piece from this thickness. From this one. Like if I am slicing it from here. Okay, so it will be divided into two equal halves. Likewise, all the planar molecule, if your groups are different as well, if all the four groups are different, then definitely this plane is always available to divide them. From the center, it is simple, like when we are opening a book, then from the center we are dividing into two parts. Okay, so there is always a plane there in the planar structures, and along with that plane, means that plane is available here, and along with that there is one more plane. If we divide, we can get the two equal halves. Here, if we divide from this plane only, then it will always have the POS. So that means planar molecules have POS, and because they have POS, so they can't be the optically active and can't show the optical isomerism. Now let's take few more examples. Like this is your 2 chloro group, and these two are the chiral centers as well. We have done this earlier. This molecule is having planar POS or not? Yes, it is having, because both the chloro, wedge means it is front side. Both the chloro are on the front side. So if we divide from the center, it's going to be mirror image of each other. Okay, so it is having a POS. POS is there. And when POS is there, there is no chance of having optical activity, even though it is having two chiral centers. Correct? Now, another isomer of the same, I can draw here, like this one. One is the wedge, means front. One is the dash. Dash means backside. Even though they both are chiral now also. Okay, so that means one chloro is on the front side while the another is on the back side. So if we will divide them from the center, what will be the actual structure? Structure will be something like that. one chloro in one half, one of the chlorine will be front side, while in another half chlorine will be pointed out back side. So they two halves are not going to be mirror image of each other. So definitely POS is not there. Okay. So if this is not having COS as well, then the molecule will be chiral and it will show chirality. So having the chiral center or not having the chiral center is not the criteria. We need to check for a molecule to be optically active POS and COS. I hope it is clear to you how to check the POS. Just divide the molecule in two equal halves, and not only divide is enough, you need to check the two equal halves that you have divided must not be the mirror image of each other. If they are exactly same mirror image of each other like this, okay, then it will be, means the two halves, if the groups are going to be superimposable, then it must not be showing the POS. Okay. So I hope it is clear to you. Mirror image means the group should be non-superimposable. If you are having the group superimposable, that means your two halves are not going to be following the criteria of not having POS. Here the two halves are having the same group. That means not actually the mirror image. They are going to be identical. Identical means same. Okay, mirror images are not same. They are equal and opposite to each other. So we want equal and opposite. We don't want same. Okay, then this is the criteria of the POS. Now next is the what is COS. COS means center of symmetry. What is it called? Okay, I'll explain you with some more examples. Center of symmetry. Okay, so what is the COS or center of symmetry? Let's take this example. If we draw a straight line from the center of molecule in two opposite straight line like this, then it should meet the similar group in the opposite direction at equal distance. Means from the center, the distance of this CH3 and this CH3 must be equal. Then this point is called center of symmetry. And it is not, should be only in one direction. It should be in all the direction. Like if from the center we are drawing a line towards the edge, then at equal distance it is meeting to the two hydrogens. Similarly, if we draw like this, from this carbon to this carbon, having the same group on both sides, and from up to down, passing through the center, it is having same group on both sides at equal distance. So such a molecule in which if we draw a straight line from the center of molecule, it should meet similar group in opposite directions at equal distance. Then in all directions at equal distance, then it is called the molecule is having COS. And what is our requirement for optical isomerism? Molecule must not have COS. Okay. So here, what is center of symmetry? A line passing through center. Line means straight line. A straight line passing through center of molecule, meeting similar groups in opposite directions, in all opposite directions at equal distance. Then molecule is said to have center of symmetry, COS. Okay. So a imaginary line that we are drawing from the center of molecule, imaginary straight line, it should meet to the equal groups or same group at the equal distance in opposite directions. And it should happen in all the directions like in this example. Then we will say the molecule have the COS. And to be optically active, we don't want COS. So I'll give you some examples to check the POS and COS. For example, like this one. And another one also. One is the wedge, one is the dash. So yes, in this molecule there are the two chiral centers in each. There are the two chiral centers in each same molecule. Here is the Cl group, Cl group, Cl group is present in all that. So this molecule is having the POS as well. It is having POS. If we check the COS, for the COS it is having the groups attached to the two sides but not on the third side. So that means the group will meet at the same directions or equal distance, will be similar or not. It is not having COS. You can check easily from the center of molecule. If we are passing through this side is no molecule. So definitely it is not having COS. But because of having POS, the molecule is chiral. Molecule is not chiral. Because one of the things is present. I want, so no optical isomerism. Okay, so it will not show any optical isomerism. In this case, in the trans case, we are having, in the trans case, we are not having the POS. I already explained to you earlier. There is POS is not present, as well as COS is also not there. You can easily check the COS from the center of molecule. If you are passing the line, then it is not meeting the same group in opposite directions at the equal distance. So both are not present here. So compound will show optical isomerism, correct? Because your compound is following the criteria of being chiral. So this is a chiral molecule. This is a chiral molecule. So it will not show. It will show optical isomerism. So let's take few more examples. Now the point is clear. To check the optical activity, you need to check the two things simply. POS and COS. Don't think about the chiral centers. Both are having two chiral centers, but they both, out of these two, one is non-optically active, no optical isomerism, while the another one is having that. So I'll give you some more examples for the optical isomerism, but I think the point is clear. Having chiral center is a different criteria, and among that also one condition you need to remember. If you are having a single molecule, let's suppose I am having the lactic acid here, in which only one chiral center is there. So what I told you, when you are having one chiral center, then it will be essentially a chiral molecule. POS, COS will not be there automatically, and your molecule will be able to show optical isomerism. So here, no need to waste the time to check the POS and COS. Both are going to be definitely absent all the time. So remember this point always. When there is only one chiral center, then it will be always optically active. One D and one L isomer will be there. This is the lactic acid. Another one will be the mirror image of that. Out of the two structure, one will be D, one will be L. But if your molecule is having more than one chiral center, you need to check the POS and COS. If any of these are present, then your molecule will not be chiral. Correct? So let's take few more examples and finish the topic. So guys, let's take this example to check the optical activity or whether it is showing or not. So first of all, what we are going to check, we are not going to check the chiral centers, but it's better if you check, if somebody asks you, you can check that too. But to show optical activity, what we need to check? POS and COS. These are the two things essentially enough to be checking the optically active or not. So here in this compound, there is one Cl, one methyl. Is there any chiral center? No. Because molecule is symmetrical. With respect to this, the methyl is having the equal position on both sides. With respect to methyl, Cl is having equal position from both sides. So definitely there is no chiral center. And moreover, in this molecule, if we check the planarity in the molecule, so definitely this POS is not there, groups are different, but we are having the POS from this direction. Means half of the methyl upside, downside, half of the Cl in two portions, then it will be having the POS. And POS is there. If we check the COS is not there because the groups in opposite direction are going to be different, so definitely COS is not there. If we check optical activity or optical isomerism, because POS is there, it will not be optically active because we want both of these to be absent. Now check this. In this molecule, this is not a chiral center. These two are going to be a chiral center. And if we check POS, COS and optical isomerism in all that. So if we check POS, definitely the POS is from this direction may happen if the Cl would also be there. But there is only one possibility, we should draw a line through the Cl. Let's check if we are drawing the line through the Cl, then one of the methyl is wedge, means front side, while the another one is back side. So these two can't be the same half. Two halves must be similar. So that means it is not having POS and definitely COS is also not there. So it will be optically active compound. Clear? Now in this case, if we check POS and COS, let's go to the point clearly. They both have two chiral centers because one of the chlorines and another chlorine are not going to be symmetrical. That's why these two are going to be the chiral center in the molecule. And in this molecule, if we try for the POS, you can easily see that the chlorines group are, one is the wedge, another one is the dash. If we try a line passing through the center, then it's not going to be the equal part or similar halves. Because one group is going to be front, another one going to be the half. That's why this is not having a POS. And if we check for the COS, then COS is also not there because the equal, if we pass a line from the center, then equal distance, no similar group are there, so COS is also not there. And if POS and COS both are absent, then definitely it's going to be a optically active compound and will form the optical isomers. Okay. Now next example is the cumulene. Cumulene we have already studied in section of the geometrical isomerism. Cumulene are compound having the continuous double bond. And in the chemical bonding, we have already learned that double bonds, continuous double bond or double bonds more than one are never found in the same plane. If one of the double bond is in axial plane, then another will be in the equatorial plane. So definitely the group attached on the terminals will also be not in the same plane. If one side group are present on the front back, means wedge dash, then another one will be the top and bottom. So likewise, if the molecule is having even cumulene, then the group will be non-planar to each other, and when this system is there, there will be no POS and COS is also not there. You can see the molecule, and when both are not there, then your compound is going to be optical active compound and it will show optical isomerism. So here just do one thing, write a note. Even cumulene are optically active compound if terminal carbon have two different atoms or groups. So even cumulene are going to be optically active compound, will show optical isomerism if it is having the two different atoms or group, and there is no problem if the same set of atoms and group is repeated on the another side, but no two should be same on the one carbon. Correct? This is the another case which is odd cumulene. Odd cumulene, just go through about the structure. Let's suppose this pi bond is the axial, then this will be equatorial, and the next one will be again axial. That means the terminal pi bonds are going to be the same. So terminal carbon are going to be having the same structures, and group aligned to them will have the same configuration. Maybe both sides they are having the wedge dash configuration on both sides, or maybe front back. Okay. So in this situation, what's going to be present here? In case of odd cumulene, there will be POS. Means you need to treat these compounds. Like the simple double bonded compounds. Like in the simple double bond, we always have a POS, even though groups are different or atoms are different, doesn't matter. We always have a POS passing through the center of the molecule. Like this, we can bifurcate the molecule. So it is the same type of system having the POS, even though COS is not there. So it will be optically inactive compound because of having POS. Okay, but odd cumulene will show the geometrical isomerism. Now, spirane, these are called spirane system. Spirane are same as the double bonded system. Likewise, the two pi bond doesn't lie in the same plane. Two rings also doesn't lie in the same plane, connected through a sp3 carbon. Those are spiranes. So if one ring is axial, then another ring will be equatorial. So if the axial ring is having the group like that, front and back, then this would be having the group on the top and bottom. And if the terminals are having the different atoms or group, this side methyl hydrogen, two different atoms and group are present, maybe same set repeated on this side or different. If you are having the even spirane, then due to having the different configuration of the terminal carbon, one axial, one equatorial, they are losing their POS. And when POS is not there, COS is also not there, then molecule definitely will show optical isomerism. Correct? So even spirane are optically active compound. Condition is what? The terminals must have two different atoms or group. This is odd spirane. Odd spirane similar to the odd cumulene. Odd spirane, again if we see the rings. Let's suppose this ring is axial, then this ring will be equatorial. Take it like equatorial ring. This is again axial. That means the terminal rings are going to be having the same structures. So the groups attached to be in the same plane, and when planarity is there, then definitely POS is there. And when POS is there, COS, even though not there, they are not going to be optically active compound. So even spirane optically active, or spirane optically inactive compound. Now, let's see the last example. In this example, we are having the two methyls group which are not symmetrical to each other. So definitely these two gonna be a chiral center in the molecule. Now let's check about the POS. If we draw a line passing through between the groups, then we can see two halves are gonna be different, because one of the methyl will be on the front, one methyl will be on the back side. So definitely this gonna be a POS is not available in this molecule. And what about the COS? You can see if we pass a line passing through the center, then definitely both on the sides same group are not present on the similar distance. So COS is also not there, and if both are absent, then who will be present? Optical isomerism. So definitely it's going to be optically active compound will form the D and L isomers. So guys, this was about the optical isomerism, few examples. Rest is your practice. I will be available for clearing your doubts if you will send me the messages. And in the next lecture, we are going to take the next section of the stereoisomerism. That is the conformational isomerism. In this section, we will learn about the drawing projection formulas like Fisher projection, Newman projection, so Hertz projection, and their interconversion and their presentation and different projections, RS configuration, DL configuration, everything we are going to learn in the next section of this series. So please keep watching and thank you so much.